CLI and a cross-platform IDE for C and C++. Download now.
Morning, good evening, and good afternoon, everyone. Welcome to C++ Online 2026. I'm Samaresh Kumar Singh. Today, I'll be speaking about building high-performance distributed systems in modern C++, specifically using Boost.Asio and Boost.Beast. Over the last 2 decades, I have spent most of my career in building low latency distributed systems that include uh, uh, you know, systems that process millions of events per second, power edge AI workload, and support large-scale microservices. Everything here you will see has been shaped by running real production pattern that we use when building systems like API gateway, gRPC framework, distributed edge services, uh, event processing systems, and high-performance networking platform. So, by end of this talk, you should walk away with the practical building block that you can immediately apply on your own C++ systems. So let's get started. Here is a quick bit about me. I currently work as a principal engineer at HP. I have over 21 years of experience in building distributed systems, edge AI, and networking. Systems. I built the platform that requires extremely high throughput and reliability. Uh, Many of the systems I have worked on operate at scales with millions of events per second, uh, sub-millisecond latency, and 99.999% availability. On the right side, you can see my area of expertise. Um, I'm expert in modern C++, 14, 17, and 2023, uh, distributed system architecture, asynchronous networking, and more recently on the edge AI systems running close to the devices where data is born. Uh, let's get started with the actual uh, talk. So this is what we are going to cover today. Uh, this talk has been divided into four main areas. First one is async IO design. Here we will explore how IO context actually drives high performance networking, how executor and strand works, and how composable asynchronous operation works. Second, I will talk about concurrency and control flow. Here we will discuss a structured concurrency, uh, coroutines in C++ that was introduced in C++ 20, request pipelining, and back pressure handling. So back pressure handling is the something that is extremely important for any production ready systems. Third, I will talk about the resilience. Because the distributed system always fails at any point of time. So we will cover the pattern like connection life cycles, failure detection, retry strategies, and graceful degradation to stop the catastrophic failure. And finally, we will talk about the pitfalls. So these are the mistakes every software developer, or I can say most of the developers makes. Uh, and this is the problem what I have observed into the production systems. So those are the accidental blocking, hidden contention, memory lifetime bug, and some of the mitigation pattern we follow to eliminate all those pitfalls. So avoiding these pitfalls can give you 10x performance improvement, for your systems. So before we dive deeper into the architecture pattern, let's talk about why Boost.Asio and Boost.Beast uh, is considered in high performance network systems in modern C++. So this library provides the core building blocks for asynchronous, scalable, and networking applications without sacrificing control or performance. So on the left side, first we will talk about the Boost.Asio, which acts as an asynchronous I/O backbone. So Boost.Asio first implements proactor pattern. That is the first one you see here on the left side. What does it mean? That instead of application polling events or OS, uh, 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 sorry, instead of application pooling for events, the OS performs I/O operations asynchronously. When the system completes the when the operation completes, the system invokes the handler callback. Uh, this allows the small number of threads to manage thousands numbers of concurrent connections. So under the hood, ASIO uses uh, different libraries under the different platform. It uses ePOL on Unix, KCube on BSD or Mac OS, IOCP on Windows. Another important feature I would talk about is the executor model. Executor model allow you to control how tasks are scheduled, how threads interact, and how concurrency is maintained or managed. Another powerful feature I will talk about is the SEO composed operations, the third one. So instead of writing here we do, instead of writing low level asynchronous steps repeatedly, we combine them all into the higher level. So we don't have to write many number lines of code. Then fourth, I will talk about the concurrent support in C++20 that was introduced. One of the biggest improvement here we see that uh, is that network in that C++ networking is coroutine. So they allows asynchronous code to run like synchronous code. So then on the right side, we have a Boost.Beast that is implemented on top of Boost.Asio. And this provides high performance HTTP and WebSocket implementation. Some features I will talk here is about HTTP and WebSocket, the, then zero copy buffer, and then HTTP pipelining, TLS security, and then custom uh, parser that allows you to write your own custom protocol using C++. So when you combine, hello? Yes. So when you combine Boost.Asio asynchronous networking engine with Boost.Beast high performance HTTP layer, you get a powerful foundation for building API gateway, microservices, uh, edge compute systems, and high throughput distributed platform. So so far, we have looked at the Boost.Asio and Boost.Beast as a foundation layer. So let's look at the first architectural pattern used in almost every high performance networking systems. Uh, Asynchronous IO design is the one what we are going to talk now. In the high performance system, we almost always follow this architecture. Client talks to acceptor, acceptor talks to IO context, then handler and strand. So let me explain you this flow, how actually this works. When the request arrives, the system typically flows through these steps. First, client connects to the acceptor. First, second one, and which accepts the incoming TCP connections. Next connection is registered using IO context, which is essentially the event loop. The IO context monitors the socket for IO event to occur when the operation is complete. For example, when data arrives, the handler gets executed. In this case, handler is nothing but the callback function. So finally, the handler may run within the S strand, that rightmost one you see, which guarantees serialized execution without requiring mutex. And that is another biggest advantage of using S strand with the asynchronous call with Boost.Asio and Boost.Beast. So, uh, one of the very important principle here is that one thread running IO context run can handle thousands of connections. So that is the biggest advantage we get here. So let me walk you through the code. Here on the left side, you see I have created a session using enabled shared from this. That is the so this is the self shared pointer for itself. So in this, you have three variables: socket, and then flat, buffer, and a request using HTTP request, a very type. So and then we create the session using that socket, you know. So in asynchronous system, we typically build a chain of operation where each of these operations schedule the next one. So basically, if you go down, you see the run function. Run function calls the do read, and do read calls the HTTP async read function. So async read function has three parameters: socket, buffer. Means basically it tries to read the data from the socket into the buffer, and then trigger the callback on read. So this is what happens here, that when OS continues reading the data in the background, uh, you know and operation completes, the ACO schedules the handler, in this case on read. The final detail, what we see here is shared from this inside bind front handler function. This ensures that the session object remains alive while asynchronous operation is pending. So on the right side, you see the key principle. All these things works only when you follow these key principles. So, let me give you the example. If the handler gets, for some reason, if handler gets blocked for, let's say, 50 millisecond, every connection handled by that thread gets stalled. So that is, we don't want to do that, so you have to keep in mind that we never block the main or event loop handler that we run via IO context run. Second is the ownership via shared pointer. So uh, you have to use the shared pointer uh, to extend the lifetime and throughout the program, and destroy it on demand. That is when you are done. Then another one is strand for safety. Using strand, you can serialize the handler invocation without acquiring explicit lock via mutex. So this is the biggest achievement, as I said earlier. Then the another one is final one is the error propagation. So you have to do the error handling in almost every callback function, so that you know what has happened if when you are debugging the systems on its failure. So on the previous slide, we have looked into the fundamentals of asynchronous design pattern using handlers and callback. While that approach is extremely powerful, but it has a major problem. that many of us has experienced in real-time systems. So over this time, the code runs and then we get into the problem. We call it a spaghetti callback, and this is where many C++ developers struggled for many years. Uh, Traditional async code often looks like deeply nested. That is what you see on the left side of the code. What happens that you connect to the server and then send some data to write and then read data and wait for the result. You know, so but so this code on the left side looks correct, honest, but it has several problems. So first problem, what I would like to point is the control flow is deeply nested. That is what you see here. Uh, I have commented using more nesting. The second one is the error handling becomes messy. Third one is the additional steps is required to make the code, to make the code, that is, so to make the code extremely difficult to maintain. So large networking system often end up with the 5 or 6 nested lambdas or callback function, which makes even debugging harder. So all these problems, what you see on the left side is solved by using C++20 coroutine. So on the right side of the code, you see same I have implemented using C++ coroutine, using co-await function. This is the asynchronous code written like a linear form, almost like I would say synchronous code. So instead of nesting callback, what you write is first connect and then wait for completion, then write data and then wait for completion, right? So each of the synchronous operation you see is preceded by co-await. So which is the so when the operation starts, the coroutine suspends at this point. And when the operation completes, coroutine resumes its execution where it left, where it was left off. So under the hood, compiler transforms this coroutine into the state machine, very similar to callback version we saw earlier. So on the bottom, you see what we get by using the core, uh, coroutine is a stack like control flow, uh, exception safe, and linear reading or synchronous code in the synchronous code flow. Zero overhead abstraction. Compiler optimizes, as the callback, and then the cancellation support. SU provides, few APIs called cancel after, stop guard, etc. So in modern networking systems, coroutines are quickly becoming a preferred abstraction layer. Let's move to the next one. So so far we have looked at the structured concurrency with the coroutine, which helps us to write the synchronous code using C++ coroutine as we discussed in the clean and maintainable way. But writing clean asynchronous code is only one part of the story. So next biggest challenge is something every high throughput system must deal with, and that is, uh, you know, uh, we call it back pressure handling. So let me explain you the situation. Like, what happens when the system or a receiver is receiving more work than it can process. Basically, we are putting pressure on the receiver. So without back pressure handling, the system can fail catastrophically. Let me give you the example. Imagine a situation where the producer is generating event faster than the consumer can process them. If you write, you know, everything into the unbounded queue, memory usage will grow, and your program will eventually crash. So this problem occurs in many systems. That is what we have seen in the past. Uh, uh, API gateway, event streaming pipeline, message broker, telemetry collector, or whatever the microservices you see in the distributed systems. So, what is the solution for this kind of problem? The solution is simple use of bounded queue instead of unbounded one. So, in the left side of the code in the class async writer, you can see I have created a queue using deck, and that queue size is limited of 128 message. So, and then what you see that the NQ operation, we do the NQ operation there. We check the queue size if it has hit the maximum limit. If so, returns false. Otherwise, NQ the message into the queue, and then check whether we are currently writing some writing operation is going on. If not, then do the write operation and then return true. So here you can see both read and write operations are happening in parallel. So enqueue and write operations are happening in parallel. So the below one, you see the do write operation where we make a we set the writing flag to true, and then we called async write, and then there we pop the message from the queue and then do the error handling. So and then the last piece of code is just to demonstrate the producer side how it handles. So here you can see the producer side calls the produce events, and there we check if writers enqueue function returns false, means no enqueue is uh, enqueue cannot be done at this point, then we call the eld function. So, uh, what I can say, so this is the so on the right side, you can see the back pressure strategy. How we handle the back pressure. First one is use of bounded queue that you have seen in the left side of the code. Another option is using the token bucket. That is what we use in API rate limiting. Then we can also use a liquid bucket to smooth out the burst of traffic, and then we can another one is the load shedding. Here what we do, we drop the low priority work earlier, and run the high priority work uh, instead of low priority. So on the previous slide, we discussed about the back pressure, which helps to protect the system from overload. Now let's take a look into the another pattern that improves the performance, but in different way. So instead of protecting the system, this pattern helps us extract more throughput from existing uh, connections. This technique is called HTTP request pipelining, and this is the one of the cool part available in Boost.Beast. So let me explain you the scenario. In traditional HTTP workflow, communication typically follow the pattern like client sends the request, uh, server process the request, then server sends the response, and then the client sends the next request. So this creates a static request response type of cycle. So the problem is that each request waits for a response, or at least it waits for request to be completed. So this introduces a network round trip delay. which significantly limits the throughput. So what HTTP pipelining does is it allows clients to send multiple requests without waiting for a response. So here a server processes them in order and return the response in the same order. This allows the network to stay busy and eliminate unnecessary idle time. And here you see all these things has been defined in RFC 7230. Uh, in this diagram, in this design, we maintain the response queue. That is what we see in the pipeline session. We have the local variable, socket, buffer, response queue, and writing flag. So when do read function is called, we create a shared pointer, we create a request, a shared pointer of request, and then async a read gets invoked, and that there we create a response, a response, and that response is put into the response queue. And again, we do the same thing, like if no one is writing, then we do the write, and then again we do the read operation. So here you can see that multiple read operation is happening concurrently with a single write operation at the same time. And then do write function is very much similar to the previous one. Only difference is that we pop the items from the queue and respond back. You know, so we are responding. So so response is sent in the in synchronously, but by maintaining the order via the queue. So right side, you can see the throughput impact. If we don't use this kind of pipelining, we gain only 30% of the throughput. If we use four uh, uh, like you know four request pipeline, then we can achieve 70% of the throughput. In case of 70 request 16 request pipeline, we achieve 100% of the throughput. So this is the biggest gain, I would say. This pattern is particularly used in the systems like API gateway, micro service proxies, telemetry, ingestion service, edge device communication, etc. So on the previous slide, we have looked at the HTTP request pipelining, which helps us to maximize the throughput over a single connection. But high throughput system must also handle something equally important, connection lifecycle management. So in the real world distributed system, connection do not stay perfect forever, and we don't expect. Uh, and they can become idle, unstable, or silently gets disconnected. Right. So our distributed system should be able to handle all this kind of connection drop, client and or server restart, whatever bad things can happen. So when so we need some sort of connection lifecycle management, and this is what you see. Uh, uh, the connection lifecycle management first is idle, then connecting, active, and draining, then closed. So let me explain what this actually mean. So so first let me tell you that when the connection uh, so sorry, when the connection is received or connection arrives, like this that TCP handshake gets happened. Sorry, gets established. Once the connection is established, a request flow through so first of all, when the connection handshake happens, we get into the connecting state, and after that we move into the active state. And when there is no activity on that TCP endpoint, we move into the drain state, like something has gone wrong. And finally we would move to the closed and shut down state, like something, if we detect something is wrong, then we uh, close that socket, and that is very important. So let's say, here is the code example I would like to walk you through. uh, First is the uh, I have created a managed connection that have again that have the similar variable socket, deadline, and then we have two variable, keep alive interval and idle time. So basically what we do, idle for some time, like let's say 90 second, then we tear down the connection or shut down the connection, and reestablish the new try to reestablish the new connection. Keep alive interval is to make sure that the system with which I'm talking to is alive all the time. So that can be done through the asynchronous ping request. We keep on pinging the microservice and wait for the response. If that doesn't happen for 30 seconds, we consider that something wrong has happened, and then we try to reestablish the connection. So this kind of heartbeat are widely used in the protocols such as WebSocket, distributed database, service mesh, and then the cluster membership systems. So one question I would like to ask: why lifecycle management matters? So in the large scale distributed systems, unmanaged connections can cause several problems, like they can consume memory, they can hold a file descriptor, and then they can occupy CPU resources. And over the time, thousands of idle connection can accumulate and degrade the system performance. So proactive life cycle management ensures that the system remains stable under long running workload. So in the previous slide, what we have discussed, the connection life cycle management, and how to detect the failure. You know, but in distributed system, failure doesn't just happen at the connection level. They can occur when the service calls the another service. Cascading call, we can call it. For example, a downstream microservice might be temporarily overloaded, a database might be slow, network path might experience the, packet loss. All these things can happen. If we don't handle these failures carefully, a single slow dependency can cause cascading failure across the entire system. So let me explain the situation first to uh, to understand or get clarity on this you know around this area. When a request fails, the simple response is just retry immediately. But naive retry can make your problem worse. What happens? So imagine thousands of clients retrying simultaneously, and when service becomes slow, so when the service becomes slow, then this creates what is known as a retry storm, because everyone is doing a retry at the same time. So instead of helping systems to recover, this retry overwhelms the entire service. So what is the solution? Solution is a retry with exponential back off and then add some sort of jitter. So that is what you can see in the code I have I have implemented. So retry with back off. using C++ 20 coroutine. Then here you can see that we call operation coroutine, and then we catch the exceptions. Under the exceptions, we add the exponential backoff with jitter, and then finally we call steady timer. So this is the one way to protect. Second way is to introduce a circuit breaker pattern for graceful degradation. So in the circuit breaker pattern, what we do is basically uh, open the circuit. Basically, what happens that, let's say, uh, if in case some of the system is really down and it cannot be we cannot reach out after many multiple retry, then best way is stop sending requests to that system. So that can be achieved through the circuit breaker pattern, and this has three states: closed, open, and half open. So initially the state will be closed, and then like when the connection is healthy and everything is good. When connection goes bad, then we check, we try the retry uh, threshold number of times, in this case 5 times, and if we cannot reach, then we open the circuit. So next and then after some time, like uh, in this case 30 seconds, we move that circuit to half open state. In that case, we allow uh, some limited traffic to test whether that system has recovered. If not, then we move back again to the open state. If so, then if the system has recovered, then we move to the closed state, and that is how uh, circuit breaker pattern works. So on the right side, I have noted down the exponential backoff timeline. First is 50 millisecond plus jitters, then 100 millisecond plus jitters. Jitter is kind of random delay we introduce along with the fixed delay. Uh, and then 200 milliseconds, 400 milliseconds, and 800 milliseconds jitter in 5 attempts. Let's go next. So previously, we discussed the retry and circuit breaker pattern, which helps us to build the resilient distributed systems. Uh, but even when the systems are designed correctly, performance problem can still occur due to some sort of subtle implementation mistakes that developers makes. The first and most common mistakes I see in the synchronous system is something called accidental blocking. That is what we are going to talk about here. In an asynchronous system architecture that is built with Boost.Asio, everything revolves around the event loop using IO context. So this event loop is responsible for executing handler when the asynchronous operation is complete, right? So single thread running the event loop may be responsible for thousands of connections. If we accidentally block that main event loop thread, then we are blocking every connections. This often happens when developer call synchronous API inside your asynchronous handler. So here you can see in the code, we have uh, first is on read. So in the on read, we have a database query operation that is also, slow operation, takes somewhere 50 millisecond time to fetch the data from the database. And by the time it is fetching, that, entire, system is blocked for 50 millisecond. Once it is complete, then we do the write. So this seems very simple. Uh, this, so 50 milliseconds seems nothing for us, right? But if you add thousands of connections and thousands of threads, then all that 50 milliseconds gets multiplied with those numbers, and then it becomes a kind of visible problem. Second is, developers by mistake calls sleep, and they call some sort of locking and do some work. This also doesn't help. It helps to some extent, but in the production environment it doesn't help much. Then another problem we see is in asynchronous file IO, because all whatever we read or write from the disk is kind of also slow operation. It takes somewhere a few hundred milliseconds to 1 second. So these are the kind of all problem we see. So all blocking operation often appears in unexpected places. Common example I would say is the synchronous database query, file systems read, a network call to external service, mutex contention, thread sleep, heavy CPU computation, etc. So why blocking is dangerous? So blocking operations are particularly dangerous because they affect every connection, as I said, handled by the same thread, or IO context thread or event loop. So imagine a server with 4 event loop thread, and if each thread manages 10,000s of connection, then the single blocking call can result, you know i- delay in somewhere seconds, right? Somewhere in minutes also. So basically, by introducing delay, we are stalling all 10K clients connections simultaneously. So all connections are blocked. So what is the solution for accidental blocking? So this is the example or solution, you can say, I have written, uh, like how we can protect it. So first one is, we offload blocking work to the separate. So first is, whatever the blocking call we have, we run those blocking call into the separate thread pool and keep IO context thread free to run, in IO event for the IO event. So core rule of high for high performance async system is, event loop thread only dispatch IO. They never perform blocking work. So any expensive or blocking computation must run on the separate worker pool. So by looking at this code, we can think of the architecture in 3 stages. Stage one, uh, event loop reads the network data. Then in stage two, blocking or CPU heavy work execute in the worker pool. And in stage three, result returns to the event loop uh, for a response writing. So this pipeline keeps the networking layer responsive while allowing expensive operation in parallel to run in separate thread. So in many gateway systems, request handler must perform the operations such as database queries, authentication check, machine learning inferences. These operation may take milli, milliseconds of time. So offloading them to the worker pool ensures that the network layer remains fast and responsive, and that is what we want to do. So this is the pitfall number two. Is the hidden contention. Uh, we know what happens. The performance performance of the system can still collapse due to hidden contention between the threads. So how hidden contention gets introduced? One way of introducing hidden contention is introducing a global shared object, and then we try to access that object through a global mutex, right? So all the threads, whoever try to access that variable, have to wait for another thread to unlock it. So that is the another big problem. That is what we see here on request. On when the on request function gets called by multiple threads, then only one thread can get access to the cache at a time. Second one is all sharing. Here we see the we are here we have introduced the counter atomic counter of same size. All these counters belongs to the same cache line. So this is also the problem, because when this counter is getting accessed by the multiple threads, then the same cache line have to manage this counter for to support the concurrency. And the final one is contingent allocator. Here what happens, when we do bunch of allocation uh, for the memory, then that also kills the performance of the systems. So what is the solution for this kind of problem? First is eliminate the uh, so we move from the coarse grained locking to the fine grained locking. So we remove the global mutex and inject into the at the object level. So we don't acquire the lock on the global one, we acquire lock on the local data. For a cache line padding, here I have used the align 64 padded counter. There I have created atomic variable, and that is padded with 64 bit. So what happens in this case is that same at counter gets spreaded across the available variable different CPU cores, so that threads trying to acquire these counters will have their own copy. They will try to they won't contend for a single global one. And then the last one, if we really have to deal with the some sort of uh, uh, some sort of uh, heavy read, or like uh, we can, so let's consider the scenario where we cannot avoid the locking. So what we can do, as we saw previous, we can have the read write lock. So through the read write lock, all read operation we can execute all read operation concurrently, and write operation one at a time. And then for the all memory allocation problem, what we have seen, we can have the memory pool, where we will serve the object from the pool without allocating a new one. So third pitfalls, that is the memory lifetime bug. Uh, this is the one of the biggest problem what we have seen in the production systems. So whenever our code executes or some handler gets execute, then all the local variable gets destroyed when the function ends, right? So at the later stage, when the asynchronous code try to access some of the variable that is destroyed, it results, dangling pointer kind of problem, and our program eventually crashes at that time. And then another problem is iterator invalidation. That is what we can see at the bottom of the function, where we have we are trying to uh, you know uh, erase manipulate the container. So basically we are erasing the item, or we are updating the container, and multiple if multiple threads tries to do that, it will have they will end up with the somewhere something kind of a race condition kind of problem. And in that case, either our program will crash or the result will be unpredicted. So, what is the solution? Solution is memory lifetime. Like, we have to use a shared pointer. Shared pointer uses a reference counted mechanism, and that is where we control lifetime of the variable, so that variables gets destroyed only when we try to uh, when no one is using it. Basically, when someone uh, so whenever the shared pointer gets accessed by someone, its reference count keeps on increasing by one. And if there is no reference to this shared pointer, this gets deleted. So that is how we control the lifetime of the uh, variable. So up to this point, we have looked at the series of individual design patterns like asynchronous I/O, coroutine, back pressure handling, pipelining, lifetime management, retries, uh, how to avoid blocking, and then managing memory lifetime. So here we are going to put all together and see, like, uh, e- e- what each of those component does. So in our distributed systems environment, we have client, we have gateway layer, we have processing, and then we have upstream services. So on the client uses client communicate with another services using HTTP or WebSocket or gRPC, right? Uh, Then at the gateway layer, we have acceptor pool, TLS termination, rate limiting, and authentication via J- JSON Web Token. So then at the processing layer, we have a request router, middleware chain, back pressure control, and circuit breaker, all we have discussed. Upstream services can have microservices using HTTP, DB cache, via Redis, MongoDB, whatever you can have, Cassandra, message bus, we can have Kafka, ZeroMQ, RabbitMQ, etc. So, and then ML inferences using gRPC. So, bottom one is the production number. If you follow the pattern, what I have discussed earlier, using that pattern, you can achieve more than 5 million event per second, and latency will be somewhere less than 500 microseconds. You can manage up more than 50,000 concurrent connections, uh, m- four times more thread, and we can have, zero copy buffer. So we don't do the copy. We just move the uh, items. So this is the composable building block we should have. So apply this pattern to any RPC gateway or edge services you are implementing. Have asynchronous IO or use asynchronous IO with STRAND. You always prefer to use C++20 coroutine. Handle the back pressure the way how I have shown you in the example. Then al- uh, you know allow HTTP pipelining, to send uh, one response for multiple requests. Life cycle management, retry with circuit breaker, avoid blocking call, and then lifetime safety using the shared pointer. So finally, here are the takeaway. First, you should prefer asynchronous call using Boost.Asio and Boost.Beast. Then prefer coroutine over the callback because coroutine is faster than the callback because it has a cool feature called pause and resume. and it restarts from where it was ended. Uh, then back pressure is mandatory handling. So you have to, be prepared to handle the back pressure using a bounded queue, avoid using unbounded queue because that will lead you to out of memory problem. Never block the event loop. The IO context run is the event loop. You don't have to block because that manages thousands of connection. If you block, then entire thousands of other threads will get blocked. That is controlled by that event loop. Lifetime is kind of everything what we say. Have the controlled lifetime of all the object you see. So I would recommend to use shared from this whenever you are constructing any class, and use the shared pointer to control the object's lifetime. Resilience is engineered, so retry with back off plus jitter, circuit breaker, and graceful degradation. This really helps. So yeah, so that's all about the I have to share with you, and how you can make performance efficient systems. Here is my LinkedIn. You can connect with me if you have any questions. I'm ready to answer now.